Okay, now I call this x1 of t in anticipation of the fact that we're going to put another ball on another incline moving in the opposite direction. We're going to have an x2 of t. So to be consistent, I should have called this v1 of t and a1. Okay, but okay, I'm being a little careless, but we can clarify that next. Okay, well, I tell you that if v of t equals at plus b, then since v of t is the derivative of your x of t function, now you've got to know a little bit of calculus, and if you don't, ignore what I'm saying. But if you know a little bit, you probably ought to think about what I'm saying here. And if you're in the Physics 231, you'd better think about what I'm saying. Okay? Your velocity is the derivative of your position. We've talked about why that is, we've defined it, and we'll do even more with it. So what is this the derivative of? Well, if you had 2 semesters of calculus, or even 1 semester of the calculus course that's usually taught in the first semester, as opposed to 1 semester of just differential calculus, which is also a valid course, then you pretty much know that you do the antiderivative and you get this. Okay, and people have already done that without being prompted. So, a lot of people know the calculus quite well. You can verify, if you only know differentiation, that the derivative of this is this. And then you can ask yourself, well, if I know this, how would I find the function that this is the derivative of? You can probably think that through. But if you've only had 1 semester of calculus, well, actually you're eligible for the Physics 231, so you will want to think through that. If you're not in the 231, you don't need to worry about it. Or university physics. If you're in a college physics, you don't need to worry about it. Okay, anyhow, there's a very simple reason why this is your position function. Now, c is your integration constant. It could be any number, because when you take the derivative of this, the derivative of c is 0, so it's not going to affect the derivative. So you can always have any number here at all when you do this antiderivative, but for any given motion, this c is going to have a specific value. Okay, so okay, v of t is at plus b. A, as we saw, is 15 centimeters per second squared, and b, your vertical axis intercept, is 0. Right there it is in this graph. We've written it down a couple of places. So we plug those into this form, and we get 1/2 15 centimeters per second squared times t squared. I admit I didn't write that t squared when I wrote this down. I'm pretty bad with clerical details, and it costs me, but something has to go when you get older. I'm almost 30. Okay, and then we have 0 times t, because that's b. And then we have c, which is undetermined. But we're going to determine it very quickly here. So that comes out 7.5 centimeters per second squared times t squared plus c. Okay? Well, now, what information do we have that will allow us to determine c? Well, we do have the information that we want to set this up so that the position is 0 at t equals 0. Well, x of t is the position, x1 of t is the position function. So x1 of 0 is going to be 0 centimeters, right? x1 of 0 seconds is 0 centimeters. But of course, x1 of 0, according to this formula, is 7.5 centimeters per second squared times 0 squared plus c. And this is just 0, multiplied by 0, you get 0, so you just end up with c. So x1 of 0 equals c, and x1 of 0 equals 0. What do you conclude about? Man, I get choked up when I get excited. Okay, what do you conclude about c? It's got to be 0. It's got to be 0, sorry. So c is 0, and x1 of t is just this. Now, in a minute, we're going to have another motion in the opposite direction, on the same x scale, but starting at a different point, moving in the opposite direction. So we'll see how to handle that.